Okay, so in today's video we're going to cover Riemann sums. Now, what Riemann sums basically entail are that if I, for example, were to take the area between a point A and a point B on a curve f of x, I can use the definite integral f of x dx between the limits a to b to get that area. But what the Riemann sum basically is that this is exactly equal to the limit of n approaching 0, n approaching infinity, of the sum from k is equal to 1 till n of delta x into f of x subnotation k. Now, this looks convoluted and kind of confusing at first, but as we go through our example and we kind of learn where this is derived from, it becomes more understandable. So we're going to start off by looking at a graph of x squared plus 1. We're going to take that as f of x. So I have a graph right here, and this is going to be x squared plus 1. This is a bit janky, but you get the idea. So now I'm going to say that I want to find the area from x is equal to 0 till x is equal to 4. So I can break this up into pieces 1, 2, 3, 4. So this is 1, 2, 3, 4. And this is f of x is equal to y. Yeah. So this is f of x is equal to x squared plus 1. So basically what happens when we do integration, and in this case a Riemann sum, is when we're doing a Riemann sum, we basically assume that if I want to find the area of this curve between A and B, I'll say that 0 is my A and 4 is my B. If I want to find the area of this curve, then I can approximate it by making rectangles like this. So I can make a rectangle. I can make 4 rectangles, and this may not give me the exact area, but this can give me a good approximation of the area between 0 and 4 for this curve. But there's multiple ways of approaching this. So what I did here was the way you do it with the left Riemann sum. And what happens in the right Riemann sum is it starts from the right hand side, as you would expect. And we'll discuss how this works basically. But the point I'm trying to make here is that in a Riemann sum, what we're doing is we're making rectangles between two given limits, and we are deciding the number of rectangles. And since in this case I made 4 rectangles, if I, for example, let's say n is the number of rectangles, so if I did n is equal to 4, then that will give me a kind of okay approximation. But if I did n is equal to 5,000, for example, which is a really big number, obviously, but if I, for example, hypothetically did n is equal to 5,000, then that would give me an even closer approximation. So what we're basically doing in Riemann sums is that this whole formula here is basically us trying to find and calculate the areas, the sum of the areas of all of these rectangles. And the reason why we take the limit of n to infinity is, in this sum, the n basically denotes the number of rectangles. So if I take n to infinity, what that does for me is that lets me have an infinite number of rectangles, and that obviously means that I will have the exact area under this curve. So now we're going to discuss left Riemann sums, right Riemann sums, and midpoint Riemann sums, and how they work, and we'll derive, kind of understand what the Riemann sum means, the formula itself means. Okay, so now we are going to talk about the left Riemann sum. and we're going to make the exact same thing we made before, the curve that we had before, which was x squared plus 1, and we're going to integrate it. We're going to find the sum, we're going to find the area under that curve from 0 to 4. Now, how I want you to think of this is, imagine that the width of, first of all, what is a left Riemann sum before we talk about anything else? A left Riemann sum, what that basically entails is that we start from the left hand side. So if I want to approximate the area under this curve from 0 to 4, if this is A and this is B, 0 is A and 4 is B, then the left Riemann sum is basically saying that the height of the rectangle is going to be the height of the initial point. So basically, if I'm taking 4 rectangles between 0 to 4, that means that it's going to be 0 to 1, 1 to 2, 2 to 3, and 3 to 4, right? So what that means is that for an increasing function, a left Riemann sum will give you an under approximation. Because look at how it looks. When I'm drawing these rectangles, the starting point is where we start from, right? So the left is where we're starting from. So when it goes from 0 to 1, it's going to have the height of the function at 0. And I drew the graph a bit weirdly here, but it's going to be more apparent when we move towards the right. And from 1 to 2, it's going to have the rectangle is going to have the height of the function at 1. So you can kind of see the gap that's creating. And once we move more to the right, it's going to become even more apparent. So we're making the sum here. And you can see the gap kind of widening in that regard. You can see that it's kind of blank here. Like I have these areas that are left uncovered. And this is why it gives me an under approximation of my area. And now we're going to discuss the actual Riemann sum. So if this, let's say I have a rectangle, this is a rectangle. I'm going to say that the width of this rectangle is going to be delta x. And since all of these are in equal intervals, it's from 0 to 4, and for simplicity's sake, I took 4 rectangles, then all of these are always going to have a width of delta x, okay? And the number of rectangles kind of determines delta x in that regard. So how do we calculate delta x before we even talk about sums or anything? The simplest way, obviously, to calculate the width of a rectangle will be to take the upper limit, which in this case, I'll mark them. This is A and this is B. So the upper limit, the delta x, will be the upper limit minus the lower limit over n, where n is the number of rectangles that I want to use to approximate the area. And the reason this makes sense is, let's use this practical example. If I'm taking the sum from 0 to 4 and I want to make 4 rectangles, then it's going to be 4 minus 0 over 4. That means that the width of one singular rectangle will be 1. So this is why this delta x formula works. And when we do the limit for n to infinity, we use this formula in terms of n. We let the n stay n. But that's for another time. So this is what delta x means. And if I want to find the area of any of these rectangles, I know that for 0 to 1, it's this rectangle. For 1 to 2, it's this rectangle. For 2 to 3, it's this, and so on. So from the left Riemann sum, will I not take f of x for 0? Because we just discussed that when we move from the left, that means we take the point that was the initial point on the left. So for this rectangle, the initial point is 0. For this, it's 1. For this, it's 2. For this, it's 3. And this is ending at 4. This is not the initial point. So we don't take another sum from 4 because we want to find the area till 4. So that's why in a left Riemann sum, we take 0, 1, 2, 3 in this case, and when we study right Riemann sums, it's going to be 4, 3, 2, 1, and it's not going to be 0 because that rectangle will end at 0. So yeah, that's why we don't take the final limit as a point. So if I want to find the area of this rectangle, I know that delta x is common. It's the same for all of them, but the height of the function is different at every point. So for this rectangle, since it's the left Riemann sum, the initial point is 0 for this. And that means that I am going to find f of 0. F of 0 would be the height, right? And that means by the same logic that for this rectangle, it's going to be f of 1, the height. For this, it's going to be f of 2, and for this it is going to be f of 3. So another way we have of writing this, when we write this in some notation, we kind of try to make it a bit more easier for ourselves, is that we write it as f of x subnotation k. You'll see some instances where it's written as, many instances where it's written as f of xi, but I choose to write k because some people can confuse I as iota, and that can become a bit confusing for some people. So now if I want to find f of xk, then let's just ignore the k for a minute, or let's just keep the k, why not? But if it's f of 0, then can I not say that it's gonna be a plus k minus 1 into delta x? I'll explain this, why it's this way. Let's look at the formula for the Riemann sum. It was this, right? It was sum from k is equal to 1 till n, ignore the n, into f of x k times delta x. This part is obviously kind of self-explanatory. This is basically the height of the function into the width of the function. So basically f of x into delta x will give me the width of one, the area of one rectangle, right? So basically what this means is that, let's say I'm taking the sum, let's ignore this, and it's from 1 till 1. Then if the sum is from 1 till 1, it's only going to be one thing, right? So that means it's going to be f of x 1 times delta x. Delta x in this case was 1. And if I'm taking 1 here, that means that it's going to be f of x1 is equal to a plus 1 minus 1 times delta x. And that gives me f of x1 is equal to a. And what this basically means is that for the first thing, it's not f of x1. Sorry, I apologize. I kind of confused this a bit. It's not f of x. I apologize. This is just xk. I should have elaborated that before. Yeah, this is just xk. So it's saying that x1 is a. Now x1 being a basically means that I'm finding the height of f of a and multiplying it by delta x. Ignore the function we were looking at, but this is basically what's going on here. And now what happens is that this is basically what's happening in the formula. Okay, so we're gonna solve this first in terms of just the sum. Let's ignore the terms we know for our sums and whatnot, because that can kind of get confusing for us. But if I want to find the area of these four rectangles, I will obviously add all of them, right? So it's gonna be f of 0 times delta x plus f of 1 times delta x plus f of 2 times delta x plus f of 3 times delta x. So f of 0 for x squared plus 1 is just 1, so 1 times 1. F of 1 for x squared plus 1 is 2 times 1. F of 2 is 5 times 1. F of 3 is 9 plus 1, which is 10 times 1. So this gives me 1 plus 2 plus 5 plus 10, which is 7 plus 1 is 8, so 18. So this is what I'm getting from my left Riemann sum when I evaluate it directly without kind of looking at the sum. This kind of helps you look at the logic instead of just looking at the sum and following the formulas. And now we're going to look at the definite integral from a to b, which was 0 to 4, of the same thing. And we'll see, hopefully, that the left Riemann sum gave us an under approximation of the actual area, because integrating gives us the exact area, right? So if we integrate this, we get 4 cubed over 3 plus 4 minus 0 cubed over 3 plus 0, which is obviously just 0, so we can ignore that. And 4 cubed over 3 is 64 over 3 plus 4. So 64 over 3 plus 4 gives us 25.333. So notice how the exact area is 25.33, and our left Riemann sum gave us a value that was lesser than the exact area. So we saw this diagram on the diagram, and we also calculated this. So now we see that the left Riemann sum gives us an under approximation of the actual area. So now we're going to look at the right Riemann sum, and then after that finally the midpoint Riemann sum, so that we can finally look at the limit to infinity of it. So the right Riemann sum is exactly the same thing. It's not much that's different in it as well. You have the exact same curve. We're going to take x squared plus 1 for this. And we're going to take the limits from 0 to 4. 1, 2, 3, 4. So now on the left Riemann sum, on the right Riemann sum, I apologize. We're going to start from the right, obviously, because it's the right sum. And on the right sum, we're going to see that since we start from the right, we take the height from the point we're starting, right? So the height for 4 is till here. Now notice how much of this rectangle is outside of this curve. So this is why the right Riemann sum gives me an over approximation. This is how the rectangles will look when we sum them. And again, since we're using the same number of rectangles and we're using the same limits, we know, to save time, that delta x is equal to 1. And we're taking the limits from 0 to 4. So we can simply add these rectangles. This is what happens when we're doing a Riemann sum, right? So when we add the areas of these rectangles, it's going to be, since we're starting from the right, it's going to be f of 4, it's going to be f of 3, f of 2, f of 1. So it's going to be f of 4 times 1 plus f of 3 times 1 plus f of 2 times 1 plus f of 1 times 1. So f of 4 is obviously going to be 16 plus 1, which is 17 times 1. This is 10, this is 5, and this is 2. So now what we get is 17 plus 10 plus 5 plus 2. This gives us 34. So now we see and we've observed that the right Riemann sum is giving us an answer of 34 when the exact answer is something along the lines of 25.33. Yeah, so the exact answer is equal to 25.33. So we've observed that this is a blatant over estimation of the actual area. And in terms of the right and left Riemann sums, we also have the midpoint Riemann sum. So in the midpoint Riemann sum, it's basically the exact same thing, but instead of starting from the left or the right and ending one before each, we start from the first midpoint. So how that looks graphically is, let's say, let me draw the curve for this. So this is our graph, and this is our curve, x squared plus 1. So for x squared plus 1, we have 0, we have 1, we have 2, we have 3, and we have 4. So in the midpoint Riemann sum, what we first do is we take the midpoints between each point. So if there is going to be 4 rectangles in here, and it's from 0 to 4, then I'm going to take the midpoints of each of these points. So from 0 to 1, the midpoint is 0.5. From 1 to 2, it's 1.5. From 2 to 3, it is 2.5. And from 3 to 4, it is 3.5. So what we do in the midpoint rule basically is, when we're calculating it, is we still start from the left hand side, but now instead of the height being the height of the rectangle being the starting point, it's gonna be the midpoint. So the height is gonna be this. It doesn't really matter if you start from the left or the right, but because it's practically the same thing, because the height of the function matters here, right? So in this case, the height of f of 1.5 is here. So it's going to be like this. But if I were to take the height of 1, it would have been much lower. It would have been here. But 1.5 is here. And 2.5 subsequently is obviously here. So notice that this is giving us a much cleaner approximation. If I would have done a right hand right hand Riemann sum, then it would have been a much larger value, and if I did a left hand Riemann sum, then it would have been much lower. But this has like much less overlap in that regard. So this is probably gonna give us the most accurate, not probably, it will give us the most accurate answer in terms of a left hand and right hand, because it's more accurate. So in this case, we have delta x again is equal to 1, and the heights of the functions of the rectangles, I mean, it is the function, the heights of the rectangles are the midpoints, remember? So in this case, the area will be f of 0.5 times 1 plus f of 1.5 times 1 plus f of 2.5 times 1 plus f of 3.5 times 1. So, solving this, we have x squared plus 1, and we're going to input 1.5. So, this gives us 0.5. We input 0.5, so we get 1.25 plus 3.25 plus 7.25 plus 13.25. So adding all of these values, what I will get is 25. So now notice that the actual value of the definite integral was 25.33. The actual value was 25.33. And the midpoint Riemann sum gave us a value that is only off by 0.333, and so on and so forth. But the point is that the midpoint Riemann sum will give us the most accurate answer when we have a finite amount of rectangles, because this is basically um, giving us the most accurate height. It's not overestimating way too much, and it's not underestimating way too much. But obviously, it's still not the exact answer. So now we're gonna evaluate definite integrals using a Riemann sum with the limit of n approaching infinity, and we'll see, hopefully, that we get the exact same answers. Okay, so now we're gonna do a Riemann sum that equates exactly to a definite integral. So we're gonna say 1 to 4 x squared plus 7x plus 1 dx is exactly equal to the limit of n approaching infinity of the sum of k is equal to 1 till n, and this is going to be delta x times f of xk. So this is obviously the same sum we've been doing the whole time. The limit of n approaching infinity basically means that we're taking an infinite number of rectangles. So it doesn't matter if you do the left Riemann sum, the right Riemann sum, or the midpoint sum, because in the end you're going to get exactly the same answer, hopefully if you do the calculations correctly. So in the case of delta x, we know delta x is equal to the upper limit minus the lower limit over n. So upper minus lower over n, which is 3 over n. And we know that x of k is equal to, now we can use the left or the right or the midpoint one for this. I prefer the right because it's much more simpler to remember. So it's this, a plus k into delta x, and a in this case is 4 plus k in this case is k. Yeah, k in this case is k. So this is k over 3, k into 3 over n, and this gives you 4 plus 3k over n. So this is your x into k, x subscript k, and now we're gonna find delta x into fxk. So delta x times f of x subscript k is 3 over n into, firstly we're just going to write it in terms of the function notation, so it's going to be delta x is equal to f of, delta x times f of 4 plus 3k over n. So this is how it should look, 4 plus 3k over n, and wait, yeah, I seem to have confused this. This isn't A, this is B. I accidentally wrote B. This is 1, so this is gonna be 1. All of these are 1. The B is 4, A is 1, because it's from A to B. So yeah, it's gonna be delta x into f of 1 plus 3k over n, and delta x is 3 over n. So now we're gonna expand this fully, and what you get is x squared in the place of x squared, you plus 1 plus 3k over n squared plus 7 into 1 plus 3k over n plus 1. So this gives you 3 over n is 9k squared over n squared plus 6k over n plus 1 plus 7 plus 21k over n plus 1, which further simplifies to 3 over n times 9k squared over n squared plus 27k over n plus 9. So now I have my expression for my summation, and I can now write this in the sum, and I'm going to first expand the sum and then I'll kind of solve the whole thing, you know? So you have the sum. We're not going to apply the limit right now. We're going to apply it when we're at the exact final step. So the sum from k is equal to 1 to n of 3 over n times 27k squared over n squared, 27k squared over n squared. Sorry, it's 9k squared over n squared plus 27k over n. So it's 9k squared over n squared plus 27k over n plus 9. So now notice in this that the summation is in terms of k. So n in this case is treated as the integer. Because the n is a integer value, k is the value that's changing. So we can treat n as an integer and we can take that as a common factor. So I'm going to write this as 3 separate sums, and I'm going to take n and any whole number common. So 3 times n in this case is 27. N times n squared is n cubed. So this will give me the sum of k squared. This is adding into 27 times 3. This is 81 over n squared. Again, the same sum. K is equal to 1 to n of k. And 3 over n times 9 is 27 over n. So this is 27 over n. Sum of k is equal to 1 to n of 1. So now I can further expand this. You should remember the formulas for your sums. Obviously, they have their own derivations, but when you're calculating, you need to know. So k squared is 1 over 6 times n into n plus 1 into 2n plus 1 plus 81 over n squared plus half n into n plus 1 and 27 over n times n. So these two cancel. What I'm left with is 27 n into n plus 1 into 2n plus 1 over 6n cubed plus 81 into n plus 1 over 2n squared plus 27. And now I'm going to apply the limit. So I'm going to write the limit first, limit of n approaching infinity of this whole term, 27n into n plus 1 into 2n plus 1 over 6n cubed plus 81 into n plus 1 into 2n squared plus 27. Okay, so now I want to look at and kind of teach you how you can evaluate limits like this. It's something I learned from someone else on YouTube, but basically instead of expanding this whole thing and then looking for the terms that in which n cancels out, we can just look at the numerator. So in the denominator I have n cubed, and in the numerator the maximum power of n can be only n cubed. So that means anything that is not n cubed is going to become approach 0 as n approaches infinity, right? So I see that n 27n times 2n is 54n cubed. So I'm going to write that, and I'm going to ignore the other terms because I know that they're going to approach 0 as n approaches infinity. So it's this. The n cubes cancel, as you can see here. And then in 81 n into n plus 1 over 2n squared, you see n into n is the highest power. So it's going to be 81 n squared. And this is over 2n squared. So n squared cancel. And we have 27 as just a number, so that's not going to be affected. And as you can see, if I were to multiply the whole thing, I would see and observe the exact same thing, that all the other terms would have a value of n in the denominator that would make the term approach 0 as n approaches infinity. So that's why we can just ignore that and help ourselves in terms of the calculations. So 54 over 6 is 9. So you get 9 plus 81 over 2 plus 27. So 9 plus 81 over 2 plus 27 is equal to 76.5. And now, just to confirm we've done everything correctly, we're going to integrate the expression we had as a definite integral from 1 to 4, x squared plus 7x plus 1 dx gives us x cubed over 3 plus 7x squared over 2 plus x from the limits 4 to 1. So you get 4 cubed over 3 plus 7 into 4 squared over 3 over 2 plus 4 minus 1 cubed over 3 plus 7 into 1 squared over 2 plus 1. So when we evaluate this, you have x cubed over 3 plus 7. So we have x cubed over 3 plus 7x squared over 2 plus x, and then we plug in 4. That gives us 244 over 3 minus, when we plug in 1, we get 29 over 6. So we do 244 over 3 subtracting 29 over 6, and we get 76.5. So that means we've done everything correctly, and this is basically the whole logic behind definite integration. When you integrate something, it may be as simple as what I just did now. Like, the definite integral of this was barely 2 or 3 steps to solve. But the Riemann sum with n approaching infinity is basically what's going on when we solve an integral. It's taking an infinite number of rectangles and it's finding the area of each one of them. And since it's an infinite amount, it means that the area is going to be exact. It's not going to have a over approximation or under approximation. So that is basically how Riemann sums work. And thank you for watching, and let me know if there's anything else you guys want to see videos about. I find calculus interesting, so I decided that this could be something that people would find fun to watch and learn from. Thank you for watching.